Hi, everybody. Possibly you can hear me. Let me get on this camera and swing it. You're getting a live look at our guest, Ian Stone. Ian, would you mind saying hi just to double check your audio here for a second?
Hello.
How did the morning go? Who did you meet with this morning? Was it all a blur?
Yeah, it's a bit of blur, but I met all the people up in Panga and got to learn all about the real-time GPS network that's run out of here in Central Washington University. Really amazing work.
Hey.
Much more complex than I ever thought it would be.
Oh, wow, that's cool. Oh, you're saying all the right things, you know, to promote us here. Hang on just a second. Let me get an iPad and see your live chat comments and just make sure we're doing okay. But welcome if you can see us and hear us. And this is our first time, you know, so it's going to be me thinking out loud here for the next 10 minutes or so. If you're watching the replay, it is 11:48 right now. And if you're watching in replay, go ahead and skip ahead 12 minutes. That will be the start of the program. But in the meantime, we're going to say hi to a few folks, just like we've been doing in the backyard long ago. And I got to find us here first of all. Struggling with the iPad at the moment, but let me ask, I'm looking at the live chat on the monitor. Are we 5x5 with both Nick and Ian? Could you please text that in, live stream people? And let me find this stream.
Hey Nick,
Yes.
do you mind if I bring my bike and put it on the side here?
Go for it. 5x5. Thank you. And can you be specific one more time? I'm going to talk to Ian and just double check. I'm nervous about that. So, Ian, is everything? So, Ian, when were you last passing through the valley? Where were you headed? Do you remember?
Yeah, I was headed out to the gorge. I think it was June or July. I went to go see, I think it was Above and Beyond.
Above and Beyond?
Yeah.
Is that a festival or a group?
It's a group. Yeah.
Okay.
Yeah.
Well, I'm feeling my age at the moment, Ian. Come on now. But what a setting, huh? I mean,
yeah,
come on.
Beautiful.
Yeah.
Beautiful. Looking right up the river.
Nice. Thank you for that. And thank you for that. It looks like we're doing okay. Let me just say hi to a few of you as folks start trickling in. And I'm going to, that's great. I need to relax. So far, so good. So, yeah, where are you viewing from? Can I say hi to a few of you as people kind of filter into the room, and we'll eventually kind of swing around maybe and give you a wider shot. Hello, Swamper60 in Marlborough, Massachusetts, and Grangeville, Idaho. Relax from Finland. Thank you. I needed that. Lake Ozark, Missouri. Butler, Missouri. That's 2 Missouris in a row in case you're keeping score on your card at home. Spokane, Washington. Birmingham, UK. Los Angeles. Hi, Don. Good to see you again. Regine in France. Stoke-on-Trent, UK. I think I know what that means. Germany, Norway, New Zealand. Smoke-free Seattle. Yeah, that front came through, didn't it? Everybody's feeling much better about the air quality. Corvallis, Oregon. 100-Mile House, British Columbia. Grants Pass, Oregon. I almost want to show you this, but maybe it'll make you more nervous. I don't know, like, you know. So here's these folks chiming in.
Oh, wow, Australia.
Yeah. Crazy.
Impressive.
Huh? Hi, Ian from Hobart, Australia. Yeah.
Heard you say Birmingham, but it's the other Birmingham.
Oh, yeah.
Birmingham, Alabama is my hometown.
Oh boy. So roll tide. Is that what I'm supposed to say?
Yeah, roll tide. Mhm.
Okay. Well, hopefully nobody's from Auburn, Ian, or we're gonna see a change in your demeanor. There she is. You're gonna sit in your spot almost.
Almost.
I'm gonna be sitting close to you here.
Okay.
That's perfect. Thank you. Yeah, let me. I don't know. I'm trying to decide now. Do I swing you around? Oh, why not? Let's have you. I'll say hi to a few more of you from across the way. Let's try that.
Does it show? Yeah.
Yep. Framed up on Jordan's shoulder. Please continue chit-chatting like nothing's going on here, please. Tim, make small talk, would you? Hi, Melissa. LeGrand, Oregon. Papagino, hello. Still saying hi to folks. Where are you viewing from? I'm a little further away, but I think we can communicate. I just wanted to give you a sense of the room here. Nice looking crowd. Chris Mattinson in his off-camera position. Chris Mattinson safely in the shadow zone. Oh, look at this guy. All right. Wisconsin Rapids, hello. Seattle. Okay, now everybody's listening to me. Okay, I can't do that. This is a little far away, but I realized that my power cord wasn't working properly, so you're a little bit further away, but I hope you'll be fine.
Okay.
Okay, good. Give me another second here. I'm going to set up my other iPad. No big deal. Thank you all for joining us. If you just joined us, we're starting the lecture in about 7 minutes.
Like a very it goes across the irrigation behind my hall and it's metal.
Backcountry Gary, hello.
It's a metal
Are you smoke free?
and it but every going on it. Can you take a picture on it?
Is this a new talk or a combination of new and old? Or?
It's a combination of new and old.
Good. That's
Yeah.
comforting. We'll try out a few new things, I guess. Huh?
Yeah, it's fun because I was able to do a little bit more research on just like the history of faulting in Washington, like what we've known about in the last century.
Nice.
Which, so that's all new stuff for me, at least.
And maybe part of that was prompted by me emailing and saying, hey, can it be a little bit more general or something? I don't know how. Was that kind of the impetus to throw a little bit of context in, maybe?
Yeah. Most of these research talks, you go in and you jump immediately right in, and within 10 minutes, half the audience is asleep.
Exactly.
So, yeah.
Exactly. Thank you for saying that. Good. I'm trying to get away from that. And yet we do want it, we do want some meat and potatoes, which I'm sure you have for us. But yeah, I mean, the days of a speaker talking to 2.5 people, 10 minutes in, like you say, I mean, come on, what are we doing?
Yeah.
Nice. A little bit more with you, and then I think let me just kind of think out loud with you here for a second. So I think what I'm going to do. Hi, Bree. Right now. About on their way out to do it, or
No, just raise your hand and get it to them. You gotta make sure that
can I do it now?
But yes, go.
Okay. Hey, we got about 5 minutes before we're starting. Bree has some forms. If you don't know anything about the forms, can you go talk to her right now, please? It's forms about being off camera versus on camera. I guess you need to fill out the form either way. Everybody needs to deal with your form. Okay. If you haven't dealt with a form with Bree, 2 weeks ago. Please deal with her right now before we start. Just letting you know, if you saw this 2 weeks ago, Nat hit the end stream button right away, but I wanted to do a little bit more with you after the talk. And so I think that's my plan. As soon as Ian is done with his talk, there'll be some live Q&A between Ian and the room. And then I'm going to keep the stream going after we're done with that. And I'm not sure, but I think maybe I'll come back like this and do a little live Q&A with you. And then if Ian's handy and not swamped with people talking to him individually after the talk, maybe Ian will come and try to answer a few of your questions. I don't know. We'll play that by ear. But I appreciate you being here. 426 people? Not bad. Not bad. I think I'm basically saying I'm about done talking to you directly, and I'll see you after the talk. Thank you for being here for the very first Talk Fridays guest lecture. You need to get out, Pete?
No, I'm okay.
Okay.
You sit right here and be
Okay. All right.
moved here 3 months ago, and I've been moving rocks for 44 years. Someone carrying around. Yeah, saw that rock there. Oh, that's it.
Well, I'm going to do a sweep outside, kick people inside here, and then I'll do a quick intro. And also, there's these forums. There's concern about people being on camera, not wanting to be on camera, that sort of thing. And then we'll get rolling.
Great.
Thank you.
Yeah.
Hot mic. Yeah, Garrett. How'd this week go? Good. Pretty much in here. Oh, Tyler, Geology 101. Tyler, you're back. Nice. Food and everything. Yeah, if you want to go for it, and you can go large. I'll get that on the screen as soon as I'm done with the intro talk. Yeah, yeah.
One thing I've gotten kind of good at was this is the fake flowers I took a picture of. And then, because I make my cake cover. And that's all that I did. Yeah, I had to do that for like 5 seconds.
Well, good afternoon, everybody. Thank you for being here. It's great to have such a large crowd for our first guest speaker of the quarter. And there's more guest speakers coming, so let me quickly give you a sense. Next week, Nicole Rocco from Pacific Northwest National Laboratory in Tri-Cities. She will be here, the life of a dark matter chemist, geochemist, a friend of Hannah. So Hannah's going to be doing the introductions next week. 2 weeks from now, Will Hoover, University of Washington, episodic tremor and slip in a chemically reacting shear zone. That's 2 weeks from now. Also, Hannah giving the intro to that. Then we have Veterans Day, no school on Friday, so we skip a week. Then the Friday before Thanksgiving, November 18th, Joel Gombiner, University of Washington, Moses Cooley mega floods. Then off for Thanksgiving, and then the final Friday, the final day of regular classes. Hi, Jeff, Vinman's Bakery. Megan Miller, who started here in the geology department 30 years ago. Her talk will be Timing and Navigation, One Woman's Path. So that's the slate, that's the schedule this fall, and we will be in person for each of these, and I'm glad that you're kind of falling into the rhythm of this. Yes, there's paperwork. Yes, there are forms to deal with. Just to remind you that I'm not going to bother right now, but this half of the room, kind of a diagonal line, this half of the room is on camera regularly during our sessions, but this half of the room is the shadow zone where you're never on camera. So if you prefer that, totally fine. But please deal with Bree on the way out if you haven't dealt with some paperwork. Are we good? Can we thank Jeff at Vindman's Bakery one more time for the free goodies? What was the hot seller today? Was it focaccia? Was it the pizza-like things?
I was just out there, 4 empty boxes.
4 empty boxes. Your generosity continues. Thank you, Jeff. Okay, a quick introduction, and we go right to our speaker. This is Ian Stone from the campus of University of Washington, United States Geological Survey, Alabama native, grew up in Birmingham, undergraduate, Colorado School of Mines. Robin, there we go. She just graduated. All right. So, and then on to the University of Washington for a PhD under John Vidali and then Aaron Worth, postdoc at UW, and now still at UW, US Geological Survey. So Ian's talk today, earthquakes on Washington's crustal faults. Let's welcome Ian.
Thank you, Nick. Appreciate it. So yeah, as Nick said, my name's Ian Stone, and I am a postdoctorate researcher at the US Geological Survey. Most of what I do is looking at crustal earthquakes here in Washington, modeling them, and using that to back out seismic hazard characterization. So today I'm going to share with you a little bit of information about earthquakes on Washington's crustal faults. There it is, over there. So presenter view.
We're on a presentation thing.
Let's see.
Sorry.
Can I switch it over? Back to that. All righty. Let's see.
I'm learning, Ian. We should have tested that out. I'm sorry. That's my bad.
That's all right. No problem.
So while Ian is,
Let's
go back to wide.
Play from start.
Oh, you need it up there. Of course you need it up there. Hannah to the rescue.
I might.
Yeah.
Chemo gal.
Just hit swap displays at the top.
And knows.
Go back.
Top left, swap displays.
Oh, on this laptop, okay.
Oh,
Really? No.
can I do it? Oh, someone has it.
Yeah, who's doing that?
Never mind.
Is you controlled on that one?
So it's, you need the mouse. Let me give you, you've got a different mouse than I
Let
do.
me try one more thing.
Everything's, you're in total control with that green thing. Whatever you do, Hannah, there is,
Sorry. No, Ann, what's your suggestion?
Yeah, just that, not record,
Rehearse? No.
no, you don't want presenter. I just play from start.
It's the way that it's this. Hold on. Can we do?
Craig, are you here?
Thought I
Display
knew
settings.
things.
Maybe.
Yeah, go to display.
I don't know that you want to change any of that because you can break the,
Okay. We're changing something here?
no.
Okay, yeah.
Craig to the rescue.
Well, I
Sorry,
the
Ian.
PowerPoint
Sorry.
probably better than, I think all you folks know it as well.
Viewers, do what you can to hang out. Sorry about this.
So you were trying this guy and it's putting it into.
Yeah, and a mouse was floating around on here a minute ago, but I don't know.
Okay, so this is what you're wanting, yes?
Yes.
Okay, so that,
Oh, let's see here.
actually, I'd say,
There we go.
Hey,
Thank you, Craig.
thank you. Alrighty. So where were we? All right. Regrouping. My name is Ian Stone again, and I am from the USGS in Seattle. I am a seismologist, not a computer scientist, as has been made clear. So today I'm going to share with you some information about earthquakes on Washington's crustal faults. In the first part of the talk, I'm going to explain what crustal faults are with respect to the other sorts of, or crustal earthquakes are with respect to the other sorts of earthquakes that we have here in Washington State, and discuss why it's so hard for us to characterize some of the older earthquakes that we have here in Washington. And then in the second part of the talk, I'm going to talk about how we characterize seismic hazard at the USGS in Seattle, and go into a little bit of information on the research that I'm doing there now. So part one, again, we're going to answer the questions: why do we have crustal earthquakes here in Washington? What causes them? And when have they happened here in the past? So if you've ever seen any of Nick's talks, I'm sure you've seen a diagram like this before. It's in pretty much any talk anyone ever gives about the Pacific Northwest that involves earthquakes, but I always include it because I think it's good to provide the context of what sort of earthquakes we're talking about. So the first sort of earthquakes that we have here in the Pacific Northwest are interplate earthquakes. These happen between the Juan de Fuca and North American tectonic plates, and they help facilitate motion between the two plates. In the past, we've had really big ones of these. In the year 1700, for instance, we had a magnitude 7 earthquake, and every 500 years or so, we have a magnitude 8.5 or above earthquake, so they can get quite large. The second major type of earthquake that we have here in the Pacific Northwest are deep focus earthquakes. And as their name suggests, they happen very deep, between 300 and 100 kilometers down inside of the Juan de Fuca plate. The actual causes for these sort of earthquakes is a little bit of a mystery. The running theory right now is that it's related to a chemical change that happens when the plate is put under a lot of pressure and heat, and a rheological change happens that squeezes out a little bit of water and allows for a brittle fracture to happen, and then you get these rather large earthquakes. The last big deep earthquake that we had here in the Pacific Northwest was the Nisqually earthquake, which happened in the year 2001 and had a magnitude of 6.8. But there's also been large deep focus earthquakes in 1949 and in 1965. And the third type of earthquake that we have, and the one that we will be spending the rest of our time on for this talk, are crustal earthquakes. And these happen in the actual crust of North America and are rather shallow. They happen between 0 and 20 kilometers. They can get as deep as 30 kilometers underneath the Puget Sound, but most of the time they're pretty close to the ground surface. And the last major big earthquake that we had in the crust here in Washington State was the Intiat earthquake in 1872, and I'll talk a little bit more about that later. How do these crustal earthquakes differ from the other sorts of earthquakes that we have, other than the fact that they're in the North American crust and they're shallower? Well, generally speaking, they're more abundant. Looking at this map over here, we can see that they tend to happen pretty frequently. Since 2010 or so, we've had several dozen magnitude 3 earthquakes, 3 or above earthquakes in Washington and Oregon. And generally speaking, as you go down a magnitude level, you increase the number of earthquakes by a factor of 10. So there's hundreds of magnitude 2s that have happened in the same amount of time and thousands of magnitude 1 earthquakes. That said, larger earthquakes aren't super common. If you're talking about magnitude 5 or above earthquakes, those happen maybe once every decade or so. And on a given fault, you might only have a magnitude 5 earthquake once every few thousand years. So the very big earthquakes are relatively uncommon. And in these cases, the shaking tends to be more localized, at least relative to, say, a megathrust earthquake, which would cause shaking all the way up and down the coast. Or like a deep focus earthquake, a large one, would typically cause shaking all the way up and down the Puget Sound. These tend to be, the strongest shaking tends to be right next to the actual fault itself. That said, the shaking can be much, much more damaging. Say a magnitude 7 next to downtown Seattle would do much more damage in Seattle than a magnitude 9 megathrust earthquake would, probably. These crustal earthquakes, they can happen pretty much anywhere in the Pacific Northwest. Any place where you have the crust getting deformed, you can have a sizable earthquake of some sort. That said, we do tend to see earthquakes clustering in a handful of locations. In this region, we tend to see more earthquakes, for instance, in central and western Washington than we do, say, down in Oregon. Looking again at this map over here, we can see that the majority of these have happened in around the Cascades and in the Puget Sound region, and they taper off by the time you get down to Portland or so. Which is odd. Why do we have this variability? To understand that, you need to take a zoom out to look at the entire region and look at the tectonic context of the entire Pacific Northwest. And I know that Nick talks about this a lot in his videos as well. Broadly speaking, the entire Pacific Northwest is rotating clockwise relative to the rest of North America. And this is largely motivated by the translation of the Sierra Nevada block, which is down in Northern California. It's getting dragged up to the northwest. And as it's doing so, it's running into another crustal block that's in Central Oregon. This large block is known as the Siletz terrain, and it's relatively thick, rather well consolidated. It's about 30 kilometers thick, and it's a bunch of oceanic basalts that kind of got tacked on to the side of the continent. And it all tends to move in one consolidated mass. It's not very prone to active deformation. So that's also being pushed up to the north and west. And as it does so, it runs into Western Washington. Western Washington is underlain by an amalgamation of various terrains. It tends to be weaker than the terrains that are down to the south. So it's feeling this pressure from the south from these other terrains, but it runs into British Columbia, which is pretty well solid with respect to the rest of the North American continent. So as a result, we see a lot of compression here in Western Washington. It's sort of getting accordion crushed. And because of that, we have lots of faults and lots of earthquakes. And this is reflected in the sorts of faults that we have here in the Pacific Northwest. Most of the large major faults that we have are reverse faults. So if you know what a reverse fault is, it's when the two pieces of crust are going together and they kind of smash together and you have reverse motion on them. The largest faults that we have that are of this type are on the west side, the Seattle fault and the Tacoma fault. And over here, we have all the faults associated with the Yakima fold and thrust belt. So these are accommodating that reverse motion. We also have a lot of oblique faults. These are similar to thrust faults in that they can accommodate this reverse motion, but they're also accommodating some of strike slip motion, so side to side. And that accommodates that northwestward translation. So the slip sense on all of these faults that we have primarily accommodates this northwestward compression and translation. So I mentioned that we do occasionally have larger earthquakes. Over the past 150 years or so, there have been approximately 15 earthquakes of magnitude 5 or greater. Again, we can see that these tend to cluster around central Washington and central western Washington. But occasionally we can get them in other places, like this one that happened down near Walla Walla in 1936. So again, you can have largest earthquakes pretty much anywhere. And there's one on here that really stands out. It's the 1872 magnitude 7.2 earthquake that happened up near Intiat, and I'll talk a little bit about that now. So this earthquake occurred late in the night of December 14th, 1872, and it is the largest earthquake that's happened in Washington since European settlement. The region was pretty sparsely populated at the time, but there were eyewitnesses to the earthquake near the actual epicenter. And here we have one over here to the side from the Washington Standard in 1873. It says the peaks of several of the hills of the Kittitas and the Columbia Range of the mountains were hurled over and broken. Trees were crushed to pieces. Great masses of earth, as if from a tremendous landslide, rushed down the mountainside and mixed with stone and wood. And the people thought that the entire Grand Tool country was sinking. So a pretty apocalyptic scene that was going on out here at the time of that earthquake. Of course, the shaking was strongest next to the actual epicenter, but the earthquake was felt as far away as Montana. It was strongly felt in the Puget Sound area, and it was felt as far north as British Columbia, as far south as Oregon. Interestingly, we didn't actually really know where this earthquake happened until very recently, and that's kind of an interesting story. The earthquake itself happened in the Cascades, and since it was late or mid-December, there was lots of snow, very rugged terrain, and there were lots of landslides associated with the earthquake. So at the time, nobody could really pinpoint exactly where the earthquake happened. And its location thwarted us for a while. A lot of people tried to locate the earthquake using felt reports, but most of the felt reports were from like the Puget Sound or from Walla Walla. And that meant that we couldn't really figure out where exactly it was to any sort of certainty. They thought it could be anywhere from the Canadian border down to like the Columbia Plateau. But a persistent swarm of earthquakes that was happening off of or between Chelan and Wenatchee sort of gave us a hint about where it might be. Finally, in I guess 2020 or so, a new study was done using LiDAR, which is short for light detection and ranging, which goes out and creates these really high resolution topographic maps of the mountains. And using this method, they were able to identify a fault scarp, or where they think the ground actually broke during the earthquake. They went out and tested some organic material that had been caught within the fault scarp, and as well as in a landslide that they assumed happened during the earthquake, and were able to see that this fault scarp happened sometime around 1873. And just to emphasize it, it might be kind of hard to see. That's where the scarp is on that map there. So you can kind of see it with your eyes once you look at it a little bit. So the fault itself is located in Spencer Canyon, which is a few miles south of Intiat. And one of the reasons it was so hard to find is that it was partially buried by a landslide that happened at the time of the earthquake. When they actually went out and measured it, it looks like around 1.5 to 3 meters of slip happened at the surface, which is consistent with a high magnitude 6, low magnitude 7 earthquake. And just to prove that paleoseismologists aren't a bunch of idiots and can't find a 6-foot tall fault scarp, this is what the fault scarp looks like from, well, in real life. So I guess if you were to ask me where a fault was in this picture, I'd say, okay, well, there's kind of a valley here. That kind of looks like a fault scarp, or maybe it goes down along the river here. But really, that's where the fault scarp is. So it's fairly well hidden in the terrain. And this kind of outlines a problem that we have here in the Pacific Northwest with finding some of these older faults. So we know that we can have largest earthquakes here. And we've probably had even larger earthquakes in the past, but how do we even figure out about those? For a long time, people didn't think Washington could host these large earthquakes. In fact, here's a quote from a scientist at the University of North Carolina. He was giving a talk to the Seattle Chamber of Commerce in 1920. He said, because of the glacial drifts within Seattle, the city is immune from earthquakes for all time. And in fact, there are no sharp faults which can make for serious seismic disturbances here, which today we know that is absolutely not the case. There's faults all over the place that can cause largest earthquakes. But again, this emphasizes a problem that we have here. To show you what I mean, I'm going to do a side-by-side comparison of two faults. On the left here, we have California's famous San Andreas Fault. And on the right, we have the Seattle Fault. So I want you to put on your geomorphologist hat for a second and try to identify the faults in these two pictures. So take a minute to look at that and think about it. Where are the faults? All right, so let's start with the San Andreas Fault. Let's see here, where's the fault in that? If you said that, congratulations, you're qualified to be a seismologist in the state of California. All right, now let's try the Seattle Fault. Where's the Seattle Fault in this picture? Well, oops, spoiled it. Well, if I was going to say anything, I'd look at this lineament here. That kind of looks like a fault. Or maybe this shoreline here, that's pretty straight. Maybe that's a fault. Well, in reality, the fault runs through right there. And if you were able to pick that out just by looking at it, congratulations, you deserve an honorary degree in geomorphology. But again, it's pretty hard to find these large faults in Washington, which has been why we haven't known that this place can host big earthquakes for until very recently. And just to emphasize what exactly makes it difficult for us to find faults, there's several reasons. First is that there is abundant vegetation. So if you're trying to find a 2-foot tall fault scarp, but your region that you're looking at is covered by hundreds of thousands of 20-foot tall trees, you're not going to be able to pick it out very easily. Urbanization tends to pave over any fault scarps that we might have. So particularly in places like Seattle and Tacoma, where a lot of developments happened in the last century, you tend to just bulldoze over any scarps that we might have. Probably the biggest factor is active surface processes like glaciation. Any large earthquake that has caused offset in the Puget Sound or the Cascades before 16,000 years ago, evidence of that has been completely wiped away. It got bulldozed by glaciers, so we don't know about it. Any offset that we see now has only happened in the last 16,000 years. On top of that, we have relatively low deformation rates. I made the comparison to the San Andreas Fault a minute ago. That wasn't really fair. The San Andreas Fault, it accommodates a couple centimeters of slip per year. Whereas in Western Washington, we're talking about a few centimeters of slip per decade. So we aren't having large earthquakes every decade or so, or not every decade, every couple centuries or so to generate large fault scarps. And then on top of that, not all earthquakes really leave clear evidence that they've happened. A good example of this is the Northridge earthquake that happened in 1994. It was a magnitude 6.7. Killed several dozen people, caused $20 billion of property damage at the time, and it never broke the surface. It was what we call a blind thrust earthquake. So if you were just looking for fault scarps, you wouldn't actually be able to know that an earthquake had happened there. There are some caveats here. For instance, we know from Native American oral histories that large earthquakes have been happening here for millennia. And using these oral histories, we can often get like a generalized location for where an earthquake happened and the timeline based on like how many generations back the story has been passed down. But these are really only broadly approximate with respect to magnitude and which fault that the earthquake happened on. So it's often difficult to back out recurrence rates, for instance, from this sort of oral history. So with that in mind, how do we figure out when past large crustal earthquakes have happened here in the Pacific Northwest? Well, we have several tools to help us do some detective work to do that. The first and probably most commonly used tool is radiocarbon dating. Radiocarbon dating looks at the proportion of radioactive carbon isotopes in a particular piece of organic material. Sometimes you can get organic material entrained inside of a fault scarp when rupture happens, or maybe a tree gets buried in a landslide or something. And you can look at the proportion of that radioactive carbon and from that back out an age of when it died. And that's been commonly used here in the Pacific Northwest. Another common one that's used is dendrochronology. So say, again, a tree dies in a landslide or it gets drowned in a lake. If the stream gets dammed, you can then compare the record of tree rings in that dead tree to live trees that were living during the time of the event and back out an actual date for when that tree died in the earthquake. Another method that we often use here is landslide and turbidite dating. A particular phenomenon here in the Pacific Northwest that we get commonly, at least in geologic timescales, are large volcanic eruptions, which often leave ash deposits that cover the entire region. And if you can place, say, a landslide or a turbidite, which is like an underwater landslide, between two of these ash layers, then you can bracket the age when that landslide happened, which might be caused by an earthquake or something. And then more recently, we've been using LIDAR, which again is light detection and ranging, which can, the method, it uses lasers to range find to the ground. If you do it hundreds of thousands of times, you can see through the top tree layer. So it's basically removing all the vegetation from the ground surface, and it can give us a really high resolution topographic map of a given area. And using this, we've been able to see a lot more fault scarps present, particularly in Western Washington and a few more over here in Eastern Washington as well. So probably the textbook case where all of these different methods were used was dating the last Seattle fault earthquake. And it's actually a really interesting detective story. So since people have been living in and around Seattle, they've noticed several geologic oddities present in and around the city. For instance, on Bainbridge Island, specifically in and around Restoration Point, they noted that there is a large flat area that's very similar to a wave-cut platform that sits in the intertidal zone. However, this platform is well above high tide, which suggests at some point either the water level was higher or that the land dropped down. So people have been aware of that since, I think, when they first landed here in the 1800s. Later, when they went to build the ship canal, which connects Lake Washington to the Puget Sound, they had to cut through, and it dropped lake levels in Lake Washington by 10 to 20 feet or so. When they did that, a bunch of dead trees, dead standing trees, emerged from the water. And evidently, these had died in some landslide at some point in the ancient past. Likewise, there were stands of dead trees in lakes within, on the Olympic Peninsula. These had died in a slightly different way. Some landslides had been caused that blocked streams within these valleys, and they filled up and killed the trees. But all these kind of clues were existing out here, and it suggested something big had happened at some point in the past. So that had remained a mystery until the late 80s or so, early 1990s, when a bunch of separate researchers were doing projects in and around Seattle looking at these oddities. First, a scientist dated those drowned trees in Lake Washington and found that they had died at some point around 1100 years ago, 900 AD. Separately, another set of researchers looking at stratigraphy of turbidites within Lake Washington noted that there had been a lake-wide disturbance at some point around 1100 AD, or not 1100 AD, 1100 years ago. Then, when some construction was going on up at Discovery Park, they unearthed a log that had been buried in a big sand sheet. Researchers at the USGS went and dated this log using radiocarbon dating and found that it had also died around 1100 years ago. Separately, some researchers had looked at those trees that had died on the Olympic Peninsula. Also, they had died around 1100 years ago. And finally, scientists looking at marshes on Bainbridge Island noted that the marsh around Restoration Point used to be at sea level. It used to be a saltwater marsh, but at some point in the past, it had risen up and become a freshwater marsh. And they noted that the change from saltwater to freshwater also happened around 1100 years ago. So eventually all these scientists realized that they were all working on basically the same problem. They got together and noted that something had to have happened around 900 AD. And they thought the most reasonable culprit was the Seattle Fault, which runs right through downtown Seattle and through Bainbridge Island. And the date of this last earthquake was later reinforced using LIDAR. When they did LIDAR surveys of Bainbridge Island in the late 1990s, they found a large fault scarp that crossed around over the very southern portion of Bainbridge Island, and they were able to date organic material within that fault scarp, and were again able to tie it to a rupture that happened around 900 AD. So using these methods, we've been able to back out the dates of lots of earthquakes on several faults in Washington, and this work is still ongoing. The markers aren't always easy to find. You have to go out and find a lake that's been dammed and figure out how long it's been dammed and what faults are close to it and whether or not it was actually caused by an earthquake. So it's a lot of detective work. And on top of that, there's probably some faults out there that we still haven't even discovered yet, sort of like the one that was out in Intiat, which we didn't even know about until a few years ago. So with that in mind, it begs the question, how do we prepare ourselves for these large earthquakes? Obviously, if a large magnitude 6 or 7 happens under a populated place, it could cause a lot of damage. We might not know when a large earthquake can happen, but we can prepare ourselves and protect ourselves from large earthquakes. Most earthquakes are imminently survivable. It's more of an engineering issue than it is a natural disaster issue. You can build houses that can withstand strong shaking, for instance. And the way that we improve this built environment is through a process called probabilistic seismic hazard analysis. So probabilistic seismic hazard analysis, or PSHA for short, is a tool that seismologists use to estimate how strong the ground is likely to shake in a given area over a given period of time. You might have seen maps like this one over here to the right before. This is a seismic hazard map. And in specific, it's telling us 1 hertz shaking with 2% likelihood of exceedance in 50 years, which probably sounds like gibberish, but basically what it's saying is what's the strongest ground motion you would expect in a given 2,500-year period within Seattle. And that's where you get the 2% likelihood in 50 years. So it's a 2,500-year return period. And these sorts of maps are critical for construction purposes. Anytime a large building gets built, they have to reference one of these maps in order to know how strong to build a building. So, for example, say you're part of a construction firm and you want to build a 10-story tower in downtown Seattle, so right in here. And building code says that you need to build it to at least survive a once in 2,500-year event. What sort of acceleration should you then design it for? Well, you know, a 10-story building tends to have a natural resonance around 1 hertz. So you would go to this map and you would look where you wanted to build it. And based on this map, you would probably need to build it to withstand 120 to 140% G, or 1.2, 1.4 G. The return period is based on how critical the infrastructure is. Most buildings are built to, say, a 2,500-year return period. But if the building might cause extensive damage, if it was damaged in an earthquake, oftentimes you tend to build it to a longer return period. So like a nuclear reactor is built to a 5,000-year return period, which is a 1% likelihood in 50 years. The way we do this analysis is actually pretty complex and tedious, but you can break it down into 4 different main steps. The first step is going through and finding all of those faults that are likely to cause hazard. So that's when we go out, we use the LIDAR, we find all the faults that we can, and then characterize them to estimate magnitude recurrence relationships. So this is figuring out how often a large earthquake will happen on a given fault. And this can be done through a few different methods. You can use the detective methods I mentioned, looking at how often the fault slips. And you can also just use geodetic methods, looking at how much the region is compressing and then backing out what that means as far as like how often you would expect a large earthquake on one of these faults. You then have to estimate shaking from earthquakes on each one of these faults, and generally that spans a wide range of scenarios. Not every fault always breaks in a magnitude 7. Sometimes you have a magnitude 6.5, magnitude 6, and those can all cause damage. So you have to consider that when you are estimating the generalized shaking from one of these faults. And then finally, we combine the steps from steps 2 and 3 into a carefully weighted analysis and use that to develop a hazard map like this one over here to the right. So this one over here to the right, it incorporates information from not just crustal earthquakes, but also the megathrust earthquakes and deep focus. So it's pretty red over here in Western Washington, but you can see the influence of the crustal earthquakes down here. I think that's one of the, maybe that's the Lulu fault, or maybe that's a little far south. But yeah, you can see the crustal faults influence it a bit too. The research I work on is focused primarily on step 3, estimating shaking from a variety of ruptures. And I'll spend the rest of the talk talking about a little bit of my research. So when you go to estimate earthquake shaking, you can do it in a couple different ways. The most common way to do it is using something called an empirical ground motion prediction equation. And what these are is that we take tens of thousands of records from past earthquakes and use a regression such that you have an equation, you can plug in magnitude of an earthquake, your distance to the fault, other factors like the S-wave velocity at a given site, and that will tell you how strong the ground is likely to shake during an earthquake. These are pretty easy to, they're very portable, you can implement them pretty easily, so that's why we tend to see them most commonly used in seismic hazard analysis. But you can also do direct waveform simulations, and this is like a type of physics-based simulation where you directly model how the waves are going to propagate during an earthquake. I could speak at length to the relative pros and cons of using a waveform simulation over GMPE or vice versa, but I'll say here that waveform simulations tend to allow us to incorporate a bit more complexity. So we can consider the effect that a sedimentary basin might have much more easily using a waveform simulation, or how directivity might affect ground shaking or multi-fault rupture, things like topography too. These are things that ground motion prediction equations tend to struggle to model. So we've been developing more of these codes that help us accurately predict ground shaking. And so far my work is focusing on using these waveform models to simulate earthquakes on Washington's crustal faults. So I'm going to spend a few minutes talking about a recent study that we did looking specifically at the Seattle fault, which goes through downtown Seattle, like I said. We ran a bunch of different scenarios looking at magnitude 6.5 to 7 earthquakes. And what we were looking for in these earthquakes specifically was how shaking up at high frequency behaved, particularly when it interacted with surface topography. So for the model itself, it was about 60 by 60 kilometers, and it went down to a depth of 30 kilometers. The topography on it, which is what we're interested in, ranged from negative 250 meters up to about 600 meters. And the simulations themselves were run using a spectral element method code called SpecFM3D. We chose it because it tends to model topography well, and it also scales well in parallel computing settings. To run the simulations, we have to break our model space up into a bunch of little bits, and each one of these little bits we can solve for the wave equation at each time step. So this is what the mesh looks like from a distance. You can see that topographic surface imposed on top of it. And then zooming in, we can see the actual discretization of the mesh. So at each one of the corners of these mesh points is where we solve the wave equation at each time step. So as for the other inputs into the model, we need a seismic velocity model. This tells us how quickly seismic waves are going to propagate through the Earth. The particular model that we used was the USGS's Cascadia velocity model, and this incorporates data from seismic surveys that have been done across the state. And importantly, it directly considers things like sedimentary basins and fault zones, which can affect how waves propagate across the model area. The other input that we're most concerned about is the source parameters. So for the particular earthquakes that we were looking at here, we were modeling magnitude 7 earthquakes, a reverse fault. So it's again, the Seattle fault's a reverse fault, so it's accommodating this compressive motion. And for a magnitude 7 fault, the dimensions tend to be about 50 kilometers long by 18 kilometers down dip. This was something that when I first started studying earthquakes was a bit difficult for me to wrap my head around. When I was a kid, I used to think that earthquake was just an underground explosion. But really what it is slip on an actual fault plane. And the larger your earthquake is, the larger the area of that fault needs to be. In the case of a magnitude 7 earthquake, your fault plane is very large. It tends to be about 50 kilometers long and, yeah, again, 20 kilometers deep. Another thing that blew my mind when I first started studying it is that slip on a fault surface isn't uniform. Of course, by the time you get to the edge of the fault, slip has to go to 0, but on the actual surface of slip area, you can get slip anywhere between a few centimeters to several meters of slip. We don't know what that slip pattern is going to be before an earthquake happens. So when we're doing hazard analysis, we have to test out a bunch of different slip scenarios. So over here, I have a bunch of different examples of the slip scenarios that we were testing in these particular set of tests. You also don't know where the slip is going to start. Sometimes you have a hypocenter that's in the west, so it'll rupture towards the east. Or sometimes you have a hypocenter in the east and it ruptures towards the west. So we had to test out a bunch of different hypocenter locations. All in all, we had 9 different simulations, so testing out 3 different slip distributions and 3 different hypocenter locations. And this little animation over here to the right shows you what it looks like as this rupture is propagating across the surface of the fault, which takes several seconds. It's cool. So once we had all of our inputs, we were able to run our simulation. Again, for these tests, we wanted to see how topography affected ground motion. So we ran both a topography model and a flat version of the model. The earthquake that we simulated was 35 seconds long, but the simulation itself was very high resolution. So to run one simulation took about 42 wall clock hours on a supercomputer. Specifically, we're using the Stampede 2 supercomputer at the Texas Advanced Computing Center. So I'm going to show you what one of these simulations actually looks like. So here's our model area. I can take the map off so we can see the wave field here. What I'm going to be showing you here is the vertical velocity field for an earthquake that has an epicenter over here to the east side of the model. It's played at 2 times speed. Vertical velocity means it's up-down motion during the earthquake. And up here in the upper left-hand corner, I have the displacement that's happening during this earthquake. So at the station that's on West Seattle, it'll show you how the ground is actually moving during the earthquake. So the earthquake begins and rupture starts propagating across the fault surface. And then we have these very long wavelength surface waves that propagate out across the Seattle basin. And it takes actually a pretty long time for these waves to propagate across the basin. We let it restart, we can watch the displacement up here in the corner. And you have a big initial jump to the south, followed by another jump up to the north before it wiggles around a bit for a while. So it would be a very bad day in West Seattle when this happens, or if it happened. So again, one of the things that we were looking for in these simulations was how topography in specific affected the wave propagation. I have the vertical velocity field here again. On the left, it's for the flat simulation. On the right, it's for the topography simulation. Here at 5.5 seconds, there really is no whole lot of difference between the wave field between these 2 simulations. But by the time the wave has reached into the basin, we can begin to see some differences in the wave field. At 12 seconds, we can begin to see a loss of coherence in the wave front. So you can see it's starting to break up a bit in the topography model. And as time goes on, the effects of topography become more apparent. So it's starting to affect even these longer wavelength features up here in the Northwest. Another feature that we look at is peak ground motion. So what I'm showing here is peak ground velocity between the flat model and the topography model. Looking at these, you can maybe pick out a few first order differences, but it's kind of hard to tell how the peak ground shaking changes between the two. So I'm going to take the ratio of the peak ground velocity in Seattle over the peak ground velocity in the topography model over the peak ground velocity in the flat model and get this map here. So again, this is the ratio of the peak ground velocity of the topography model over the flat model. So areas where we have red, the warmer colors, indicate the ground shaking was higher in the topography model. Areas that we have blue are where we had lower shaking in the topography model. So if we begin comparing that to a topographic map, we can start pointing out some big differences between the two. If we look at a cross-section across the north part of Seattle, we can compare it to the ratio that we got in the simulations. The blue line down here corresponds to the topographic elevation across this line up top, whereas the red line corresponds to the ratio of peak ground motion. From this, we can begin to see that we typically see amplification of shaking at the top of hills and cliffs. And we see de-amplification typically at topographic lows like the bottom of channels and at the bottom of cliffs and stuff. If we look at the entire model area, we could say that on average, the peak ground shaking tends to be the same as it is in the flat model as it is in the topo model. But obviously, there's areas where we see amplification and de-amplification, and typically these are associated with areas where we have sharper topography. So shorter periods, which corresponds to higher frequency shaking, so fast shaking, over a quarter of our sites see a significant amount of amplification, over 30%. 5% of the sites see ground motion that's almost doubled what it was in the flat simulation. And then for our lower frequency shaking or our longer periods, the amplification tends to be a lot less. So larger features tend not to interact with the wave field as much, it appears. If we zoom in on a particular feature, we can see precisely how topography affects ground shaking. So this is West Seattle. It's a little triangular peninsula to the west of downtown Seattle, and it's surrounded by cliffs that are about 70 to 80 meters tall. You can see some little virtual seismograms that I placed on this feature. If we compare shaking at the top and bottom of West Seattle, we can see how topography actually affects ground shaking. So for this seismometer that we see up at the top, we can see that the ground shaking, at least for the P waves, tends not to be all that great. It doesn't really seem, the topography doesn't really seem to interact with the initial arrivals from the earthquake. However, S waves and surface waves are significantly affected, and that tends to be associated with the strongest shaking, which is kind of a bad thing because then we're amplifying this strongest portion of the shaking during the earthquake at the top of these cliffs. And then if you compare, the top of the cliff to the bottom of the cliff, you can see amplification that's close to 50%, at least at this location. So I will go ahead and wrap up there and just say that, Washington has large crustal earthquakes, not super frequently, but enough that we should worry about them. And important to characterizing this hazard is doing this characteristic or probabilistic seismic hazard analysis. And as a part of that, doing things like waveform analysis are allowing us to see how higher resolution features like topography and also like geotechnical layers are affecting the strength of ground shaking.
All right, Ian. Questions for Ian?
I
I got a question. I was wondering, with the topography versus the flat, I'm assuming that there's a velocity model difference, like a rheological, so it would relate to a rheological difference.
Yes. So the question was, between the topography and flat model, there would probably be some sort of velocity model difference. The way we handled that is that in the Puget Sound, most of the region is covered by a pretty thin veneer of quaternary materials. And the good thing about that is that the velocity tends to be kind of homogeneous as you go down with depth. So when we added topography, basically all we had to do was stretch the velocity that was in the flat model up into the topographic features, or stretch it downward in places where we had negative topography. And we don't feel as though that would necessarily affect the shaking as much as you would say, like in an area that has a lot more rocky features, maybe in the peninsula or in the Cascades.
Okay. And then the slip distributions, are those randomly generated? And did you see a difference between the three different scenarios?
Yeah, so the question was, were the slip distributions randomly generated, and did we see a difference between the different slip distributions? So yes, the slip distributions were randomly generated. We did tend to try to get ones that were a little bit more physically realistic. You notice I didn't have any slip distributions that had all the slip like piled up on one side. And sometimes when you're developing these slip models, you do get that. So we did have to pick out which ones seemed a little bit more realistic. But generally speaking, the method is randomized. And then, yes, we do see differences between the different slip models. If you have an area where there tends to be more slip, say, concentrated towards the east side of the fault, then you might see more shaking over on that side of the fault than you would on the west side of the fault. So yeah, it does affect it, and that's why we have to try out a bunch of different slip distributions to get a generalized idea of how the shaking is different. Yes?
Yeah, on the Seattle, West Seattle Fault, or the Seattle Fault crosses through so much of that South Seattle fill zones. What kind of resolution do you have on the rheology?
So the question was, the Seattle Fault passes through the south part of Seattle where we have lots of fill, and what is the resolution on the rheology that we have in that area? It tends to be actually pretty good in the south part of Seattle. Obviously, there's a lot of infrastructure down there with like Boeing Field and the port, so there's been a lot of investigation into what the actual velocity structure is within the upper 100 meters or so. So we do have a pretty good idea of that. In these particular simulations, we weren't able to incorporate that, but in this next generation of simulations that we're doing now, we do explicitly have models for the shallow alluvium and fill layers. So that is something that we are considering in our next generation of simulations.
Couple more questions? Yeah.
Yeah, I was just curious, you had a slide that had how often each fault has a significant slip.
Yes.
So there are a couple faults that you didn't have numbers on. Are they just waiting for you and your colleagues, or?
So
Have not been studied?
let's see here. Let's see if I can find it back here. This one, right? Yeah, so these were just example numbers. Every fault that we have on here does have some constraint on it. I think generally speaking, the faults in Western Washington tend to have a little bit of a shorter recurrence interval, but it's also dependent on how much investigation has been done on a particular fault. I know in particular, some of the faults over here in the Yakima Fold and Thrust Belt we're actively doing research on. I think Steve Angster, who's a new person at the USGS field office in Seattle, he's putting together a lot of trenching surveys up the road here, actually, near Ellensburg. So it's something that is better constrained in Western Washington, and we're trying to get a better idea of what's going on over here as well. Yes?
You kind of already addressed this a little bit, but in the example you gave of the bottom of the cliff and the top of the cliff being amplified or de-amplified, the bottom of the cliff is also happens to be right on or next to the water too, right? So your models don't
am I correct that they don't include liquefaction or other effects that the shaking would cause?
Yeah, so the question was, since so much of the model is at or below sea level for these simulations that we're doing, are we including things like liquefaction? And those secondary effects are things that we have not been able to incorporate yet. That starts getting into much higher frequency shaking, things like that are associated with the peak ground acceleration, which tends to be higher than what I can reach right now, at least with these simulations. These get up to a max frequency of about 3 hertz. And I think you would need to get at least to 10 hertz to start getting to PGA range. But we can amend these with something called stochastic seismograms, which use a statistical method to predict what high frequency shaking would be once you impose them on these seismograms. And then also, as we get more and more computing power, we can build finer scale meshes, which allow us to get to higher frequencies. And I think one of the long-term goals is being able to incorporate things like nonlinearity into shallow soils, which then would have a control on like liquefaction. So we're working on it. Yes?
I noticed on that same graph, there was like an amplification the seabed too. I'm assuming what the seabed is. So the red line is like a little bit higher than the blue line. Is there an explanation for that? We pointed out the peak and the bottom of the peak, but I had a question about the bottom of the bay.
Yeah. Let's see if I can find that real quick. Towards the end, right? Oh, yeah? Okay.
Now repeat the question, please.
So the question was, why is it that we sometimes see amplification under the water as well? Is that correct?
Yeah.
Yeah, so adding topography is actually, it adds complexity to the wave field in ways that aren't just first order. So yes, it's below sea level and it's technically negative topography, but you also have hills and bumps on the seafloor itself. And these smaller scale features are also going to have their own type of topographic resonance or can also trap seismic energy. So you can even get amplification on things that are below sea level or negative topography if you have like enough complexity in the surface.
How about one more?
Yeah.
So a similar question to what Bill was saying, that if I'm correct, that did we see like higher amplification of like seismic activity like at peaks?
Like at the top of hills? Yeah, yeah. Generally speaking, when you're at the top of some hill, you will tend to see higher amplification than you would at like the bottom of the hill or in a flat area. And that's because the hill has a tendency to trap some of the seismic energy as it comes up from the subsurface. You can also get improved angles of incidence. So if you have a flat surface and a seismic wave is coming up like this, it gets okay coupling with the ground surface. But if you have a hill like this and the seismic wave comes and hit, you're going to have stronger amplification on this side because you have better coupling between the seismic wave and the ground surface. So yeah, topography can amplify shape in different ways.
Wonderful. Let's thank Ian one more time.
Thank you.
If you want to talk one-on-one with Ian, come on up to the front, and we're going over to Campus Utah. Andy, you want to join us? Campus Utah, and you can visit with him now as well. So we'll see you next week. Thanks for coming, everybody.
Ribbon cliff, 1872.
I'm sorry, let me get closer.
The landslide from that is the Ribbon Cliff landslide. I think it's right north of India, and the Ribbon Cliff map here. It's cool. They must be putting LiDAR data in here because you can see.
Oh yeah, it's really high resolution.
Yeah. So Ribbon Cliff is, let's see, there's a rondo, and the fault is going up that valley. Right up here north of Antioch is Ribbon Cliff.
Oh, Was a
earthquake, it's called Earthquake Point, but that's the toe of the landslide.
Oh.
It actually dammed the Columbia briefly for
Okay.
overnight or
Wow.
two, but that cliff here, get the satellite view if it's not too dark.
That's really amazing.
Turn you off here. So I'm totally.
Okay, Ian's visiting with a number of folks, so I'm not going to bother him right now, but maybe I can just interact with you for just a few minutes before we say goodbye. Can you hear me? Am I 5x5 now? 5x5? You can now? Okay. Wonderful. Thank you all for being with us. We still have 724 people at the end of a talk. It's a huge relief that we got through without crashing the system. And I guess uppercase, you want to ask a couple extra questions? I can try to answer them. Ian's busy with a bunch of folks here, so I don't think I'm going to interrupt that flow. Most everybody is just sticking around in here and chit-chatting. And the room is abuzz. And yes, it's really nice of you folks to make specific nice comments about Ian. Of course, he's going to watch this in replay, and it'll be a nice plus for many who come here and give talks. I know Joel Gombiner just wants to have a record of his talk. He forgot to hit record during his PhD dissertation. So some of this is just for the speakers, but of course it's just nice, and you guys are generally nice as well. Did you want to say something to me?
Oh, yeah, I just want to talk to you.
Go ahead. Oh, not during the live stream. Give me a couple more minutes. I'm just about to wrap up with these guys. Okay. Yeah, I agree. I thought it was a good start, a good talk, despite our struggles at the very beginning. I'll take it. If that was our only glitch, that I will definitely take it. Okay, I think I'm going to sign off and say thank you once again. And next Friday, October 28th at noon Pacific, you can join us again, and we'll make it happen. So thank you. I love you, and goodbye.
You're getting some infinite regression there. The video behind it.
Oh, yeah. Let me end the stream here, and then we can chat. Turn my mic off.